Okay, so here we begin Chapter 7. So Chapter 7 is on a bunch of different techniques of integration. So when we're on the other side of Chapter 7, we'll be able to integrate a huge variety of functions that are currently inaccessible to us. The first such technique we're going to see is one of the most important ones. It's called integration by parts. So let's see what it's all about. Now let's consider this integral, x sine x dx. Now, of course, as always, your first question is, can you think of a function immediately whose derivative is x sine x? And nothing comes to mind. So really the only other technique that we know at this point is u substitution. And there's no obvious u substitution here. Of course, a wrong way to approach this would just be to say, oh, well, antiderivative of x is 1/2 x squared, and the antiderivative of sine is negative cosine of x. So cool, we're done. And of course, that is
wrong, 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 wrong. You're wrong, you're wrong, you're wrong.
all right. Well, what do we have here? We have a product. And we know there's a product rule for taking derivatives. And wouldn't it be nice if integration had its own product rule as well, and then we could just apply that here? Well, there is no product rule for integration. However, we can take advantage of the product rule for differentiation to come up with a technique that'll handle something like this. So let's actually look at the product rule for differentiation. So let's recall the product rule here. Well, we know that the derivative of a product is equal to derivative of the first guy times the second plus the first one times the derivative of the second. Then integrating each side would yield up to a constant the antiderivative of the left, which would just be f times g, is equal to antiderivative of each of these guys. Okay, well, if we wanted to isolate this term here, we could say that this integral here is equal to this guy minus this integral. All right, big deal. So what are we dealing with here? The principle we're going to take advantage of is we're going to assume that this here is the form of our integral that we don't know how to solve. And using this process called integration by parts, we're going to rewrite the problem as this expression here minus some new integral. And that new integral will consist of the derivative of one factor of the original problem multiplied by the antiderivative of the other factor from the original problem. So it's kind of a way of punting an integral to a new integral. Now, this is obviously a pretty cumbersome way to write this with all these f of x's and g of x's everywhere. So in practice, we have a pretty slick notation for managing this. And it looks a lot like a u substitution, but it involves two letters. So we define u to be f of x. So du is f prime of x dx. And we define dv to be g prime of x dx, which makes v simply g of x. And therefore, our original integral in terms of u and v would be u times dv is equal to f times g, which would be u v minus the integral of v du. All right. This is the form of integration by parts right here. And a helpful mnemonic here is ultraviolet voodoo. All right, so let's see how we would apply this to work out something like the integral of x times sine of x. All right, let's try integration by parts here. So when you use an integration by parts, you're going to kind of fill a little table like this. But you only make one decision, and that is choosing what to let u equal. And once you've made that decision, then du and dv and v are all determined from that one decision. So the decision you make is to let u be one of the factors of the integral. So we could let u equal x or sine of x here. And the principle is essentially that you want to let u equal a factor whose derivative is simpler than the original. So for instance, we could let u equal x because its derivative is 1, and 1 is simpler than x. Whereas if we let u be sine of x, well, its derivative is cosine, which isn't really simpler, it's just sort of a lateral move there in terms of complexity. So we're going to let u equal x here, and its du will be, of course, dx. Now we move over to dv, and dv is the rest of the integrand that you did not choose for u. So in this case, it's going to be sine of x dx. And finally, to go from dv to v, you integrate. So we're going to integrate sine of x, and v will be negative cosine of x, because that's an antiderivative of sine. All right, so what does this mean for us? Well, our integral was x sine x dx, and we now can rewrite it as ultraviolet voodoo, uv minus the integral of v du. So what is u times v? Well, that's x times negative cosine of x minus integral of v, which is negative cosine of x, and du, which is dx. So what we have is negative x cosine of x plus integral of cosine of x dx. Now it's important to understand that all integration by parts is doing is it's punting the original integral into a new integral, and you're just hoping that that new integral is simpler, or something that you can manage. And in this case, our new integral is the integral of cosine. And yeah, we can integrate cosine. So let's finish the job here. We get negative x cosine of x. Antiderivative of cosine is sine, plus a constant. So there's our final answer. All right. That seems unbelievable, so let's verify it. So we'll take the derivative of our proposed solution and see if we get x sine x. Okay, well, we're going to need the product rule for this part. So the derivative of negative x is negative 1 times cosine of x plus negative x times the derivative of cosine, which is negative sine of x, plus the derivative of the sine, which is cosine of x, and the derivative of c is, of course, 0. All right, well, negative cosine of x plus cosine of x, those guys cancel, and we're left with x sine x. So, yay, it works. All right, with our last example, we successfully solved it by using integration by parts and letting u equal x. But what if at the very beginning of that problem instead we'd let u equal sine of x, which is another factor and perfectly eligible to be u? Well, let's just see how this would play out. So we're going to go u equals sine of x. And du would be our derivative of that, so cosine of x dx. And next we come to dv, and dv is exactly what we did not choose out of the integrand, so that leaves us with x dx. And so our v is the antiderivative of dv, so that would be 1/2 x squared. And so where does that leave us in the problem? Well, here's the original. And we know this unwraps to ultraviolet voodoo, uv minus integral of v du. So let's put these pieces together. So u times v is 1/2 x squared sine of x minus v du. So that would be 1/2 x squared cosine x dx. And this is our new punted integral here. And I don't know about you, but it looks even worse than what we started with. Yes, okay. So this is what could happen if you make a bad choice in your integration by parts for u. All right, so let's firm up some really good guidelines for choosing u in integration by parts.
More what you call guidelines than actual rules.
Okay, yes. These clips today. Okay, there's a really nice mnemonic here, Lie8, which helps you choose what should be your u. So these all stand for different types of factors that might show up. So L, for instance, stands for logarithms. I stands for inverse trigonometry. So that's like arctangent of x or arcsine of x, etc. A stands for algebraic. This is kind of the catch-all one, so that would be like if you have like an x squared or rad x, etc. T is for trigonometric functions. These are the direct trig functions like sine of x. Okay, yeah, so you know what those are. And E is exponential, like e to the x and stuff like that, 2 to the x. Okay, and all logarithms, feeling sad that it doesn't have an example, so let's put ln of x in there. There we are. So the idea here is that you go down this list and that's going to be your u. So for example, with x sine of x, we would look through this and go, okay, Lie8. So L, are there any logarithms? No. Is there any inverse trig? No. Is there anything algebraic? Yes, the x is algebraic, so u will be x. And the rest just falls out naturally. You're off and running. And there it is. These guidelines are pretty good. Okay, so here we have an integral, and there's no obvious u substitution. So let's try integration by parts. Now I just want to add that if this were instead of e to the x, if this were say e to the x cubed, then suddenly that one little change makes this a u substitution problem, right? We would let u equal x cubed, so du would be 3x squared dx, and we have the x squared dx, so we'd be off and running. So an integral is not really going to be holding up a sign that says this is the technique you should be using. You need to just practice integrals and look for little clues that might lead you to a particular technique. So because there's no obvious u substitution here, we're going to try integration by parts. So we make one decision, and that is what to let u equal, and everything else will be determined from that point. So according to Lie8, we should look for logarithms. Don't see any. I stands for inverse trig. Don't see any. A stands for algebraic. Well, we have x squared. So let's let u equal x squared. So du is 2x dx. And dv is everything we didn't choose for u, so that would be e to the x dx. And v will be the antiderivative of that, which is e to the x. All right, so here's our original. And we know that's going to be ultraviolet voodoo. So u times v is x squared e to the x minus v du, 2x e to the x dx. Okay, so this is our new punted integral that we now need to work out. And let's take a look at it. Well, there's no obvious u substitution. But what can we do? We can do integration by parts again. Okay, no problem. So what should we let u equal? Well, running down the list of Lie8, we come to the algebra part again. So 2x, du will be 2 dx. And dv is everything we didn't choose for u, so that's e to the x dx. And v will be the antiderivative of that, which is e to the x. All right, so where have we left off? Well, we have this term x squared e to the x, and now we're subtracting a new ultraviolet voodoo. So that's x squared e to the x minus u times v, which is 2x e to the x, minus antiderivative of v du. So that's 2 e to the x dx. Okay, very good. And again, we've got a brand new integral. And the hope is always that it's simpler than what we had a minute ago. And indeed it is. We can integrate that one directly. So we have x squared e to the x. Let's distribute this negative. We got minus 2x e to the x plus the antiderivative of 2e to the x is indeed just 2e to the x. And that was our last integral, so let's generate the constant. And this is our final answer. You might notice that you can factor e to the x out and prefer that format, but there wasn't really much gained, so either way is fine. Okay, if you've ever wondered what function has natural log as its derivative, well, this is your moment. We're going to use integration by parts on this guy. So to assign u, we should use Lie8, and so are there any logarithms in here? Yeah, so we'll let u equal natural log, and du is therefore 1 over x dx. So dv is everything we didn't choose. Well, that just leaves dx. So what's v? Well, antiderivative of 1 would be x. Okay, so this leaves us with integral of natural log is equal to ultraviolet voodoo, and u times v, that would be x ln x minus v du. So that's x times 1 over x dx. Okay. Well, of course, that integral is just antiderivative of 1. So we get x ln x minus antiderivative of 1 is x. And let's throw our constant in, because that was our last integral. And there we are. So the antiderivative of natural log is x ln x minus x. Okay, this one promises to be interesting. So no obvious u substitution. Let's try integration by parts. So what should we let u equal? Well, according to Lie8, we should look for logarithms. We don't see any. And there's no inverse trig. And there's nothing algebraic. So we're now at the t for trigonometric. And oh, we have sine of x. So let's let u be sine of x. So du is cosine of x. And dv is everything we didn't choose. That would be e to the x dx. And v would be antiderivative of that, which is e to the x. So we have e to the x sine x dx is equal to ultraviolet voodoo, which would be u times v, that's e to the x sine x, minus v du, e to the x cosine x dx. Whoops, I needed a dx right there. Okay, so here's our new integral. And while it's certainly not any harder than our original integral, it doesn't look like it's much easier, but at least it's different. So, I don't know, let's try integration by parts. See what happens. So this time we'll let u equal cosine of x. And du will be derivative of cosine, which is negative sine of x dx. And dv will be e to the x dx. And v is the antiderivative of that, e to the x. Okay, so where are we here? Well, here's the original, e to the x sine x dx. So what is that equal to? Well, we've got this e to the x sine x term minus that intermediate integral, which is now ultraviolet voodoo itself. So that's going to be u times v, which is e to the x cosine x, minus a new integral of v du. So e to the x times negative sine of x. Well, let's just make that negative a plus and go e to the x sine x dx. And there we are. So this is equal to e to the x sine x minus e to the x cosine x. And distributing that minus gives us minus e to the x sine x dx as an integral. Okay, well, there's a new integral to work out, and no problem. Maybe integration by parts will work on that guy, right? Well, you may recognize that as the original problem. So we've gone around in a circle here, and that's going to happen sometimes with integration by parts. And when it does, there's a really sneaky move for figuring this out. We could add it to the other side. LHS being left-hand side. So if we did that, we would have 2 times this integral is equal to e to the x sine x minus e to the x cosine x. Well then just divide by 2. So we get e to the x sine x dx, this integral, which was the original problem, is just 1/2 e to the x sine x minus 1/2 e to the x cosine x. And this being our final answer, we do need to just put that constant in, and now we're done. So this little move where you do integration by parts twice and then arrive at the original integral and add it to the other side and solve, that's called the boomerang method. Okay, what about a definite integral? So remember, a definite integral has bounds of integration and evaluates to an actual number, compared with an indefinite integral, which we've been doing all day. Those do not have bounds of integration, and they evaluate to a function, or a family of functions, with a constant. All right, so we're integrating inverse tangent from 0 to 1. Well, let's use integration by parts on this guy. And according to Lie 8, we should look for logarithms. Don't see any. Inverse trig, yes, right there, inverse trig. So inverse tan of x, du will be the derivative of inverse tangent. So that's 1/1 plus x squared dx. dv is everything we did not choose for u, so that's dx. And v will be the antiderivative of that, which is x. So integral from 0 to 1 of inverse tangent of x dx is equal to, so it is ultraviolet voodoo still. However, there are still bounds of integration on this integral. But there's a little bit more going on. Let's move this guy over here. Because the u times v, if we just leave it on its own, that's going to be x inverse tan x, and that's not right. This needs to be a number. It's outside the integral. So for that part, we actually evaluate at the bounds of the integral, 0 to 1. So what is this going to look like? Well, u times v is x inverse tangent of x, evaluated from 0 to 1, minus the integral from 0 to 1 of v du. So that's x over 1 plus x squared dx. Okay, so looking at this part here, we're going to plug a 1 in for x. So we have 1 times inverse tangent of 1 minus 0 times inverse tangent of 0 minus, okay, well, how do we evaluate this integral? Well, it doesn't matter that we're in the middle of an integration by parts problem. You should look at that integral as a fresh, brand new integral. And that's definitely a u substitution problem right there. So let's let u be 1 plus x squared. So du is 2x dx, and we have an x dx. So our x dx will be du over 2. Okay, so continuing this integral, we have the inverse tangent of 1, which is pi over 4, minus 0 times inverse tangent of 0, so that's all going to be 0, minus a new integral here. It looks like 1/2 times du over u after we make all the substitutions. And the new bounds are when x is 0, u is 1, and when x is 1, u is 1 plus 1 squared, which is 2. So this guy's going to be pi over 4 minus, we can now integrate that. That's going to integrate to 1/2 ln of absolute value of u from u equals 1 to u equals 2. So this is pi over 4 minus, now we'll plug u equal 2 in, so we get 1/2 ln of 2. We don't need the absolute value, 2 is positive, minus 1/2 ln of 1. But ln of 1 is 0, of course. So we get a final answer, pi over 4 minus 1/2 ln 2. There's several ways we can write this. You could write it as pi minus 2 ln 2 all over 4. You could write it as pi minus ln 4 all over 4. You could take that and write it as pi over 4 minus ln of rad 2. So I actually just prefer the way we started, but all of those are fine. Just keep that in mind when you work out a problem and you compare it with, say, the textbook's answer. Keep in mind that when there's a logarithm involved, there's often many different ways to write the answer. Okay, let's give this one a shot. This one comes with a little hint. Substitute w equals rad x. So, okay, a w substitution, that's the same as a u substitution, but it saves the letter u for later in case we need it for integration by parts. So let's let w equal rad x. So dw is the derivative of square root, which is 1 over 2 square root dx. And so our dx is 2 rad x dw. But w is equal to rad x, so our dx would be 2w dw. So therefore, the integral cosine rad x dx becomes cosine of w, and our dx is 2w dw. So this is 2w cosine w dw. And now it does look like an integration by parts problem. So we'll use integration by parts, and good news, we've saved the letter u for it. Now what if you didn't know to use w for the substitution? What if you'd used u for the substitution? Well, if that were the case, then at this stage of the problem, you would have 2u cosine u du. And you'd still want to use integration by parts, but now we'd go u equals 2u? No, you can't do that. You would have no choice but to do integration by parts using some other letter besides u here, like w is fine. But now you have to just be careful and translate your ultraviolet voodoo into the new letters, like ultraviolet woo voo, whatever. So it's easier not to do that. So just to avoid that situation, we use W for our substitution. So you cannot reuse a letter that already has a role. And if you're looking at this problem and saying, hey, wait a second, but we let u be sine x, and then later we let u be cosine x. Well, integration by parts is not a full substitution process. It's not a full change of variables. These are just placeholders to move all the pieces to the right location, and once we're back in x here, we've relinquished u and v, so we can use them again. But that is not the case with a substitution, where this w is now in use all the way down the line. W is equal to rad x. Okay, so let's do our integration by parts. We have u equal to 2w, the algebraic part. So du is 2dw. dv is what we didn't choose. That would be cosine of w dw, and v would be the antiderivative of cosine, so sine. So our integral is now ultraviolet voodoo, and that would be 2w sine w minus antiderivative of 2 sine w dw. Well, that one's not too bad. So 2w sine w, and antiderivative of sine is negative cosine, so we get plus 2 cosine w plus our constant, and we'll just substitute rad x back in for w. So we have 2 rad x sine rad x plus 2 cosine rad x plus our constant. And final answer.